Hey guys, one sec, I'll be right back. All right, welcome everyone.
Hello.
Hello, how are you guys? Cool. Okay, so today we're gonna continue with talking about conditional probability and talk about what it means for events to be independent and really understand that in a mathematical way, not just kind of in the colloquial way or just like from English. And if we have some time, I'd like to do some examples of Bayes' theorem, and I think that would give you guys a really good setup to go work on some problems into the weekend until next Tuesday. So that's the plan for today. Let's see here. Cool. So, so let's get started. Oh. Okay, share screen. Okay, so last time we talked about how we can interpret probability as thinking about Venn diagrams and like visualizing probability as like the area of a set or the number of elements in that set divided by the total like rectangle, which is would represent the sample space. And so here's a question that I like to ask that visualizes the Venn diagrams not as a picture but as a table. So let's see here. Let's see. Yeah, this is the example I use on the test, so I'm just going to stick with it. So today's lesson will be conditional probabilities. Independence. And possibly, if there's time, Bayes' theorem. So, so here's a question. So this is the example. And a lot of what we're about to do is, if you follow that example that we did right towards the end of class, where I asked, like, given that a student is taking Mesa English, what is the chance that they're also taking Mesa Math? It's pretty much exactly similar to that idea. So at Adam Sandler university students are enrolled in drama or comedy, but not both. So according to the following table. And this is called a contingency table, because it breaks up your data set into different categories. So contingent on one category, you can see what the breakdown is. So what we're going to do is we're going to make a simple 2x2 table. This would be male students. This would be female students. This would be drama. This would be comedy. And I'm just going to put in some random numbers here. 31, 54, 27, and 72. Okay. Okay. So first question is, how many total male students are there? And you guys can message me here. Oh, let me see here. Oh, Samantha get in?
Yes.
Okay, cool. Let me see. Excellent. So yeah, 85 total male students. And how many total female students? 99. Excellent. And therefore, the grand total number of students is going to be 184. Okay. Oh yeah, Quentin, good point. Assuming no overlap, I'm going to put in here carefully. I'm going to write XOR, so they can't take both. It means only one or the other, exclusive OR. So assuming no overlap. All right. So the question is, let's try to answer the following, give the answers to the following probabilities. What is the probability that a student is male or is a comedy major? What would you do there?
And to be clear, that's OR, not XOR, right? That's,
Yes, yeah. I just put XOR for in the problem statement because yeah, you can only major in one thing. There's no double majors allowed in this school. But here you could be both a male. We do want to consider the males that are in the comedy. Excellent. Okay, so one student wrote 54 over 184, which is not bad, but that's male and comedy. So those are the males who are majoring in comedy. But we want instead, for this question is, I'll highlight, we want, we want this region. So this is the male students or the comedy students. And so you can do 31 plus 54 plus 72 all over 184. And if you did the totals beneath it as well, just be careful that you don't do, this is going to be what? This is going to be equal to 103 plus 54 is 157 all over 184. If you look at comedy, that's going to be 126, and you look at drama, that's going to be 58. So another way you could have done it is, yes, another way you could have done it is how we talked about last time. You could have done probability of male, which is 85 over 184, plus the comedy students, 126 all over 184. But you want to subtract one copy of the comedy and male students, because that would be overcounted. So either way is totally fine. Okay. Very good. Please hit yes if you're comfortable with this example. And you also see the trap. Sometimes people just add the percentage of comedy students and add the percentage of male students, and they miss the overlap. So make sure you kind of see clearly what squares you need to add together. Excellent. Okay. So that's how you could do union using this table. And now I want to introduce the idea of a conditional probability. And we did it last time. So the idea of a conditional probability is it's a probability of an event conditioned on or contingent on a subspace of living in a subset of the original sample space. So essentially what you're doing when you're taking a conditional probability is you're making your universe smaller. You're making your denominator be smaller, and your numerator might be restricted to only the parts that satisfy that condition, but are also in your new smaller sample space. So let's do a concrete example. What is the probability? So I'll write it in English, and then we'll write the math notation for it. So given that student majored in comedy, what is the probability they are so the notation for this is the probability of being a female given that we know that the student majored in comedy. So this is the probability of the event given probability of event F or condition F given we live in the universe given event C. Okay, so nice. I got a few great answers here. And Alex, do you want to explain how you got it?
Sure. So you might hear dogs in the background.
Okay.
But you know that it's given, so it means if you're just looking in that category, so just look in the category of comedy, you see that there's a total of 126 options, and we want to find out of that 126 how many are female. So that would be 72 over 126.
Excellent, nice. Pretty simple, right? So just 72 over 126. And I'm going to write a formula down and just make sure you really believe what this formula is saying. So what you observe here is that you could, instead of writing it, there's a nice formula for conditional probability, and it's the size of the, or the percentage of people overall that are studying comedy. So that could be written as the probability of comedy. And the numerator, instead of being putting in 72, this would be the percentage of people out of the all 184 that that are both in comedy, in that are female and in the comedy universe, or in having a comedy major. So these are the same expression. The only difference is like they look a little bit different, because with the numbers it would just be 72 divided by, you could, if you wanted to make it look the same, you would just make sure that it's technically going to be divided by 184. This would be divided by 184. But if you modify the numerator and denominator by the same number, by the same operation, it's the same fraction. Okay. So first, are there any questions on Alex's answer? And then second, are there any questions on the equation that I wrote down after? Do you all believe that, and just please hit yes if you do you all believe the formula that I wrote down, and how it's really the same thing as what Alex wrote, but just scaled a little bit different? Because it's just a proportion, right? It's the fraction of people that are both that are females taking comedy majors over the fraction of people that are comedy majors. Excellent. Okay, let's do another similar example with this same question. What is the probability? What is the probability of being a comedy student, given that we have information that the student is female? So let me pull that back up. So given that we know the student is female, what's the chance that they study comedy? Excellent, nice. Olivia, do you want to explain what you did?
So basically what I did is I looked at, since we know they're going to be female, I looked at the total female for the denominator, which is 99. And then we know that they're studying comedy, so that would be the 72 number still.
Mm-hmm.
Yeah, that's basically how I got it. So that would be the numerator.
Awesome. So same deal. This time the numerator doesn't change because it's still people who are females and comedy majors, but the denominator is out of all females. So given that we know it's a female in that set, what's the chance that it's a comedy? So it's just going to be 77 over 99. So I'm illustrating this example so that you pay attention to which, what is the given condition and what is the event that we're looking for. What's the event that we're looking for to find the probability of. It's very important how it's written. And I'll write here, this is still probability of female and comedy divided by, but this time it's probability of female. Okay. Any questions so far? Oh, why? Oh, sorry. It's not 77, it's 72. Thank you. Good catch. Very good. All right. So that's pretty much, the foundational building block of conditional probability. With the notation, it can sometimes get a little bit confusing, and you start to get used to it. But one thing that really, really helps me is I really kind of, when I'm focused on some sort of problem, and I either have it written out as branches or as Venn diagrams or as a table, I really kind of just like zero in on what I need and I just let everything else fade away, and I say, okay, this is my new sample space. How do I just work with this sample space? So I first identify what my sample space is, and then I work on everything from there. And that really helps me stay focused on what quantities are important. Okay, so now that we've introduced conditional probability, let's continue and introduce independence. So, and this is a part of statistics and probability that I believe is, is pretty well understood intuitively, but a lot of people, even math students, will kind of get mixed up sometimes on the, there's like a subtle, there's a mathematical definition, and there's something that just needs to be true, and there's also the English definition. So what do you guys think? What does it mean for two events to be independent?
When they don't like correlate with each other at all. Like if you roll a dice and you roll it once, the second roll doesn't depend on the first roll.
Nice. Who was that, Becca?
Yeah, that was me.
Nice, Becca. Yeah, exactly. So one roll doesn't depend, like the outcome of the second roll has no bearing on, sorry, the outcome of the first roll has no bearing on the second roll. And that's a great intuition to have. So we encounter independent events a lot in like the casino when you draw a card and you reshuffle it and then you draw another card. That's an independent event. If you roll, like if they don't affect each other, that's a good point. I'm gonna hesitate. You used a word there that's a little bit where I think gets people a little bit into trouble. You mentioned the word
Did I say correlate?
Yes,
Yeah.
yes. So
Yeah.
it turns out that there's some like weird examples. We'll study correlation later. There's some examples where you can create things that have zero correlation, but are not independent.
Yeah, I realized as I said that I was like, maybe not the best word to use.
Yeah, so that's one thing. They're like very similar, but not exactly the same. Okay, so so I'm going to write exactly kind of what Becca suggested. The outcome of event A does not affect the probability of event B. So think the first coin that you flip, the result there does not change the 50-50 idea of the next coin that you flip. So flip flip a coin twice, or flip two coins in a row. Okay. So can anyone formalize or describe this sentence using conditional probability? Can you write it? Can you give me an equation that would use conditional probability? And it's a very, very simple equation.
Probability of event A times probability of event B.
Equals what?
Equals probability of, is it A and B? I don't remember. I haven't done this in like 2 years.
Yeah, okay. Chester, you're right. We're going to jump to that one in a second. But there's an even more basic one that just literally captures the sentence. But you're right, that's going to be what we're going to get to. Quentin, do you want to share your, Kieran, you got it? Quentin, do you also want to share what you wrote?
I wrote the same thing that Kieran did. P of A given B is the same as P of A.
Nice, excellent. Well done, both of you guys. So P of A given B is equal to P of A. And do you guys see that this represents that in the first case, it's a probability given that we're in the universe where event B happened. And what it tells us is that it shouldn't have changed, it won't change the overall likelihood now of event A still happening. And I'll give you a little bit of intuition on how to think about that in a second. But one other, if we use the formula that we just found out, let me rewrite this the other way. So this tells me that P of A, the probability of A doesn't depend, is independent of whether or not B happens. So this tells us that this is the same as probability of A intersected with B divided by the probability of B. And you can also think of this as if B happens, so like if you see the coin come out a certain way, it gives you absolutely no more information or knowledge about the next event. It's as if it happened or didn't happen. Your prior knowledge hasn't changed at all. Okay, so rewriting this, you can get this rule, which we call the multiplication rule. So you have P of A. So this is the definition. This is a math definition. A, let me rewrite this here. So events A and B are independent if and only if, so this is the definition, or alternatively, kind of rewriting this formula, you get P of A times P of B equals P of A intersect B, which we call the multiplication rule. This is the multiplication rule for independent okay. Just kind of to get a good feel of what this is telling us, what it says is that, like in the Adam Sandler University example, we would say that the being male is independent of being a drama student if the overall where was it? If the overall probability of being a male, which is in the school, is 85 out of 184, so if that probability holds up in the breakdown of just drama students. So if you calculate the probability of male, it's 85 out of one. Sorry, not, what is it? Yeah, it's 85 out of 184. That's the probability of male. But what about the probability of being male, given that you're a drama student? Is that also the same proportion? So of course it's overall less students because your sample space is smaller. But if it's going to stay the same in the same like represented, if everybody's represented in each major as they are in the overall school, then we would say that the major is independent of the gender. Okay. So that's kind of one idea, that everything in each category, the different rows occur in the same proportion. That's kind of how you can think about independence. And that's an important idea because it's a little bit different and a little bit of a richer idea than just having the idea, okay, well, one coin flip didn't affect the other coin flip. While that's true, that just thinking about it that way doesn't capture the whole picture. So let me give you an example. So, and this is going to be an example where you don't know anything about what kind of events these are. Are they coin flips? Are they, it's going to be a really abstract thing, but you can tell just by checking a simple rule, this multiplication rule, you can say if these events are independent or not. So, so given the probability of A equals 0.3, the probability of B equals 0.7, and the probability of A union B is equal to let me think here. Is equal to 0.9 are events A and B independent. And the question is justify. Do a calculation, maybe like just two steps to justify your answer. So anyone have any thoughts? Can we tell, like we don't even know anything about these events. Can we tell, are they independent or not from the information that was given? And the hint is try to check if the multiplication rule is true. You're going to need to recall a concept we did like in another problem. But it was an easy concept. I think you guys were all pretty comfortable with it. Anyone have any ideas?
Well, I can kind of get how you get there. I haven't fully finished yet, but I can, if you use like the concept we did on Tuesday, where if you can rearrange the equation to find the and,
Yes.
that you then do and is P in A plus PB minus the union.
Perfect.
And so if you do that and then you find what the and is, if you take like PA times PB, you get, if you get the P and, then they're independent.
That was excellent. Yeah, so PA plus PB minus PA union B. So this statement is that thing with the two Venn diagrams, or the Venn diagram are the two sets with an overlap. There's a relation between the size of each set, the overlap, and the union. Mainly that if you add them together and you take away the union, you're left with a little overlap of the pancakes, because the pancakes, the overlap part is counted twice. There's also the rearrangement version that we did previously. But this allows you to find the overlap. And the overlap is really key for testing if they're independent. So in this case, P of A plus P of B minus the union is going to be 0.1. Now just ask yourself, is 0.1 equal to like P of A times P of B? So is 0.1 equal to 0.3 times 0.7? Well, no, because this is equal to 0.21. So I would say that they're not. These are not independent. Okay. Yeah, if it was 0.79% of, if A union B was this 79%, then when you subtract 1 minus 0.79, you get 0.21, and in that case, it would be independent. So
can you go through that one more time? Sorry.
yeah, of course. So Lacho, which case, the original problem or the comment like what would make it independent?
Just the original one, like the last 3 lines of your
Yeah.
notebook.
Yeah, so what we're doing to test for independence, we just have to make sure that the multiplication rule holds true. It's, you know what, a good way to visualize independence as well, or the multiplication rule, is like the 2 dice thing. So 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. So what's the probability of the first one being an even and the second one being greater than or equal to 4? So this is going to be so this is greater than or equal to 4. So it's half of the region. And the probability of the first one being even is also half of the region. And because they're independent, you get this nice thing that you can just say, okay, well, originally I have the orange bars, which are half of the, like, that gives me, that gives me 18 squares. And then because I know that 4, 5, 6 on the second row is independent of whatever I got on the first row, I know that it's going to be exactly half of the 18 squares. So therefore, it's going to be 1/2 times 1/2, which would be overall a quarter, and that's going to be the 9 squares of the overlap. So that's a little bit of the justification for the, or visualization of how the multiplication rule pans out. But back to our problem, in order to test the multiplication rule, in order to test for independence, all you need to do is really simple. Just check that P of A and B equals P of A times P of B. In this problem, we don't have P of A and B. We are only given the union. But if you remember that thing from last time, we can use that information to get the intersection. And once we get the intersection, which was in this case 10%, just check, is it the same, does it match up with 0.3 times 0.7? And it doesn't, so therefore it's not independent.
Can you go through the finding the intersection one more time?
Yeah, of course. So do you remember that formula? I think we did it with finding the union. We did probability of A. You add the pancakes together and you subtract the overlap. So,
Yeah.
so if you just rearrange that equation, so we saw earlier this thing. Probability of A union B equals probability of A plus probability of B minus probability of the intersection. So the right side is adding the two pancakes, subtracting the overcount. That gives you the union. You can rearrange the union and the intersection. Like you can move the intersection to the other side and subtract the union. That gives you the second equation.
And why are we able to do that? Why are we able to just flip it?
Oh, it's just algebra, right? You just subtract one and add the other piece.
Okay.
And whenever I do like algebra like that, I also like to have a visualization. So for the first equation, I think of trying to, if I have two pancakes on my griddle, and I want to know like the area that the pancakes will cover on the pan. That's like the union. So how do I do that? I add the pancakes, I stack them on top of each other, I add their areas, and then I cut out that middle overlap area. That's how I can figure out the area that the pancakes cover on the pan. And then
Okay, this makes sense.
the other equation is like, if I just want to figure out the area of the overlap, I can add together the two pancakes and kind of with my knife, like cut it so the overlap is like sitting on top of the two pancakes, and I swipe away the bottom layer, which is like the union. I don't know if you guys like, let me try to draw it here. Yeah, it's this is like that. So these are the pancakes. And then over here, there's another, okay. So I don't know. Do you guys see what I'm talking about with the pancakes? These are really soft pancakes that when you layer them, the middle part actually rises above it. And I guess these would be like, maybe I'll make this, whatever. Okay. So, yeah, so, okay, that means that's are A and B independent. So let me give you one example. You can try this one on your own. So given that P of A is equal to 0.6 and P of B is equal to 0.4 and P of A union B is equal to Let me pick a different number. Sorry, I keep picking numbers that add up to 1. This would be 0.72. Are A and B independent? Okay. And kind of the point of these exercises is to show you that the mathematical definition of independence is like just a really specific condition that is sometimes detached from our normal intuition of like what independence should be, but it does follow from like what properties we want it to have. So anyone want to volunteer to say what they got here? Nice. Olivia, why are they independent?
So first what I did was find the probability. Is it union or which one is it? Like with the upside down U? I forget what it's.
Intersection.
Oh, intersection. Okay, so to find that, I added 0.6 and 0.3, the probability of A and B, and then subtracted the probability of A union B, right? That's
Perfect.
which is 0.72.
Nice.
And then I got 0.18 or 0.18. And then to see if they're independent, you just multiply the probability of A and probability of B, and you would get 0.18. So they are independent.
Perfect. Awesome. That's it. So A and B are independent. And anytime you have independent events, it's nice to think about them as like similar to the grid thing that I drew here. It's nice to say that I can think of event, I have my entire sample space. I can think of event A as a rectangle that goes across, and I can think of event B as a rectangle that goes vertically. And the overlap is going to be the little rectangle where they overlap, and the area of that is just going to be the sides of the rectangles. And the reason we can think of event A as like a rectangle spanning across, because it's kind of like we thought about how I mentioned with the comedy and majors, the different like comedy or drama students. Like in each category, the exact proportion of male to female, if that was independent, would be constant. So you can think of it like as it's helpful to think of it as event A along one axis and event B along the other axis. And when you have the joint probability, you could figure out the overlap. Okay, so that's independent events. Here's a quick question. Last time we talked about disjoint events, events that have no overlap. And I just want to ask you this because this is a really common, there's a lot of like new definition that you guys are learning. So I want you to just think about this definition so that you can see where a lot of people get mixed up. Are disjoint events, disjoint/mutually exclusive, independent. And also, by the way, one thing you notice from this is being two events being independent, it has to like be perfectly special that like every category of one, like along one event has the same proportion of the other, like the conditional probabilities are all in the same proportion. So it's like a very special condition. Usually if you just do some things randomly, you'll find that things are not independent. But what do you guys think? Are disjoint / mutually exclusive events independent?
Only if like P, A, and B equals 0, right?
Yes. Beck, could you explain why?
Well, because Tuesday, we discussed how if A and B equals 0, like there's no overlap, that's when they're mutually exclusive. And so if you were to multiply PA and multiply PB for finding if they're independent, and PA and B ends up being 0, then they're mutually exclusive or disjoint.
Yes, exactly. And so we know that mutually exclusive means P of A, the overlap, they have no overlapping at all in common. P of A and B equals 0. Can this scenario ever equal to P of A times P of B? What's the only way it can happen?
If either of the probabilities are 0.
Exactly, good. So this can only happen, so this is like a really common true or false trap. Disjoint events are never independent. They're usually not independent unless one of the events has a 0 probability. So they're only independent if one event has a 0 probability. Okay, so that's independence. Okay, let's go on to do a little bit of stuff with Bayes' rule. So so Bayes' rule is something that's actually super relevant nowadays because it gives you a way to understand all these things with the coronavirus testing. Because it gives you a way to understand, okay, the coronavirus test came back positive. Does that mean that I actually have the virus or not? What are the chances that I tested positive and I have the virus? Because sometimes there's an inaccuracy in the virus, in the test. And the calculation of it, even if the test, when it's administered to a lot of people that have coronavirus, and it reads like 99% of the people that have coronavirus, it detects it. even if the test is super accurate in that sense, surprisingly, it could actually still have a very high chance of giving you a false positive. And we'll see that with something called Bayes' rule. So let's, and in particular, it happens when we work with conditional probabilities, and one of the events that we're working with is really rare. Well, you see that that's kind of when you get these counterintuitive results that show up. So let's try this example. Dangerous fires are rare. This is a 1% chance. So smoke let's see. Yes, that does feel a lot more like one. Does feel a lot more than 1%. So probably, but smoke is common. This is 10% chance of just a general occurrence of smoke. And then we have another piece of information. 90% of dangerous fires make smoke. So dangerous fires, out of all fires that we see, there's a lot of fires, right? People have fires on campgrounds and barbecues and all that. But unfortunately, sometimes there's really big fires. But let's assume that that's pretty rare. Smoke, you see maybe 10% of the time. Just like if you go to the beach, you might see somebody doing a cookout. And now we also know that 90% of dangerous fires, probably more like 99% of dangerous fires, but let's just keep it at 90% because I don't think you can really have a dangerous fire without smoke. But let's keep it at 90%. 90% of dangerous fires make smoke. So here's the question. If you see smoke, so if you see smoke, what is the chance what is the probability that it comes from a dangerous fire? So I'll give you guys a few minutes just to think about this, and I'll chat with you if you want to share your answer. If you need to leave early, that's no problem. So how can we think of this? Actually, hang on. So you can either draw this out with a Venn diagram, um, and yeah, let me know if you're kind of stuck or if you think you're on the right track and you got an answer. I really recommend drawing it out. It's not a bad idea. I'll give you guys 3 more minutes to think about this. Message me if you're stuck or you have some idea. So to give students who are stuck, quite a few students were a little bit stuck. So we have the case of dangerous fires, right? We have like a Venn diagram, but instead of 2 normal sized blobs, one of the blobs is really, really small, like a 1% chance. And the other blob is a 10% chance. And so we have a small little circle and we have a big circle. And there's some overlap in the circles because the dangerous fire circle also gives off a lot of smoke. So it's not a circle inside of a circle, but it's 2 circles that overlap. So let me draw this picture and hopefully that will help you get started. So we have a smoke circle, which is that. This is 10%. And we also have kind of rare, we have events that are rare. This is dangerous fires, and this is the smokes. So how could you use that to answer the question? If you see smoke, what is the probability that there is fire? So this is 10%. This is 1%. Quentin, do you want to share kind of how you thought about it?
Yeah, sure. Give me just a second to put my thoughts together.
Okay.
So first what I did is I found the amount of dangerous fires that would be producing smoke, like the overlap, which
Yes.
would just be 1% times 90%, which
Nice.
gives 0.009 or 0.9%.
Nice. So is everyone okay with that idea? That little overlap area, we know that 90% of dangerous fires make smoke. So the probability of fire and smoke is equal to the probability of fire times the probability of this is smoke given fire. So this is equal to, and I'm just using the notation here, but really, Quentin, I'm sure you just thought about it like, okay, you just thought about the sentence, right? What it's actually saying. You didn't need the formula. This is going to be a 1% chance of fire, but out of those, you're taking 90%. So this becomes 0.009. Okay, where do you go from there?
And then what you're trying to do is figure out the portion of the larger smoke circle that that intersection occupies.
Mm-hmm.
So you take the intersection and you divide it by the size of the smoke circle. So it's 0.009 divided by 0.1 because the smoke circle is 10%, which is 0.1. And that gives you 9%.
You got it. Nice. So does everyone see that? The smoke circle is 10%. So 10% of all events end up in smoke. And out of those, 0.009 come from dangerous fires. So therefore, the second question is, or the question prompt is actually asking, what is the probability of a dangerous fire given that there's smoke? We know that this is probability of fire and smoke divided by probability of smoke. This is 0.09 divided by 0.1. So I'm just going to highlight it here. This is orange. I'm going to make this one here orange. And then this would be red. Okay. And this becomes 9% chance because it comes out to 0.09. All right. Any questions on this example? So as you see here, using all these different formulas could get a little bit confusing. So I encourage you to really draw the pictures out and use them as a guide for setting up your formulas rather than just memorizing some formulas and plugging it in. The pictures really help me with the visualization. And we're going to see another type of picture that we're going to do for the main part of Bayes' theorem. But this is kind of, one thing that we also notice is that in Bayes' theorem, what you the foundation is this idea that given one conditional probability and the information about the each probability separately, you can actually figure out, you can actually switch the condition. So you can switch given A given B, you can switch it to B given A. And so the formula that we're really using here is the following. Probability of S times probability of F given S is equal to probability of F and S, which is equal to probability of F times probability of S given F. So this formula allows you to solve for one of the conditionals given the information about the other. All you need to know is the other conditional probability, like the reverse direction, and the individual probabilities themselves. So that's kind of the idea. And the nice thing is you don't need to know the thing in the middle, the overlap, because you could calculate it, but doesn't need to be given to you. All right, so let me give you another example here. Okay, so this is an example of cat allergies. And this is, we're going to do this for lie detectors, for coronavirus tests, for computer spam, all these different things. You can apply Bayes' theorem to figure out, given that your device or instrument, or you have some sort of indication that you might have an underlying issue, is how valid is that? What's the chance that you actually have that underlying issue? So this is an example, cat allergy. Hunter says she is itchy. So there's an allergy test. There's an allergy test that has the following accuracy. And you can determine this accuracy when you are designing the test, because you're doing tests on people that you would already know that if they have the allergy or not. So, so here's the information for people who have the allergy. The test says yes, or let's say it tests positive. %80 of the time. if you do not have, for people who don't have the allergy, the test might still give you a false positive, but it says positive, says, positive, says plus, or positive. And this one, I'll make it, instead of yes, I'll just say positive. It says plus, positive. It might do it 10% of the time. So there's a chance that it makes a mistake. Okay. So here's the question. If 1% of the world population has the allergy, and Hunter tests positive, what is the chance what is the probability that Hunter is really allergic? Okay, so there's quite a bit of wording here. So there's an allergy, there's a test to see if somebody's allergic. When they were doing this, developing this in the laboratory in controlled conditions, and they actually knew if people were allergic or not, they gave the test to people who were allergic, and it gave the correct answer 80% of the time. They gave the test to people who weren't allergic, and it gave the correct answer, which was negative 90% of the time, and it gave the answer positive. It gave them a false positive 10% of the time. So given the fact that cat allergies are fairly rare in the population, 1% of the overall population, and we know that Hunter tested positive, what is the probability that Hunter is really allergic? And this will be the last problem. And you could start this with a Venn diagram. What I would recommend doing, instead of a Venn diagram, because it's kind of like breaking the things up into different subcategories, I recommend trying to do a tree. And maybe on the first branch of the tree, think about breaking it up in the overall proportion of people, those who are allergic and those who are not allergic. And you actually see that you have quite a bit of information that they tell you. It doesn't seem like you have that much information, but you have information to keep working on that tree diagram. You could also do sometimes people like to do a table as well. So you can do a table. That also works, but I like to do a tree. So anyone, you don't need the answer, but anyone have any idea, like kind of want to walk through together how to do it? By the way, do you guys think that, just your intuition, how many people think that there's a really high chance, maybe like around 80% chance that Hunter has an allergy? Hit yes if you think that the chances around 80% or higher, and hit no if you think it's maybe lower than 80%. Because the test is pretty accurate, you know, it tests How many people think it's about 50-50? So hit yes if you think it's around 50-50, and hit no if you think it's a bit, if you think the chance that she actually has an allergy is less than 50. I just want to give you guys a little bit. And by the way, there's a really funny thing about this concept. A lot of doctors don't understand this concept very well because it's a little bit counterintuitive. Um, so a lot of doctors, they say, oh yeah, when this was tested, it picked it up 80% of the time. So, you know, you'll have a chance of having the virus or whatever, 80% chance that you have it, which is unfortunately a bit misguided. And like, um, there was one, who was the name of that math teacher? Somebody had him as the background.
Will Hayes?
Oh yeah, Will?
Yeah.
Yeah. I don't see the background anymore, but he sent me a really good article about like that, asking doctors about that fact, and it's something like, you know, some very high percentage of doctors, like a scary high amount of doctors, didn't quite understand this theorem. Like over 50% of doctors. Because, you know, they only have to take stats once, and then if they're just treating other stuff, they don't really have to think about this too much. So anyone, even if you haven't got it, does anyone kind of just want to walk through it together? Adam, you want to try to walk through it?
Okay.
Yeah, how did you approach it? What was your idea?
So I started out by doing the tree that you were talking about.
Uh-huh.
So I put if he actually has it and if he doesn't have it as the two branches.
Nice. So allergy and no allergy. So what would we write that? No allergy, I guess?
Yeah, I just put no.
No, okay, good. Because with these, it's also be careful with the wording, because it's like positive, negative, yes, no, just it can get a little bit confusing. Okay, and what percentages are there on these branches?
Well, so if he actually has the allergy, then it's 1% chance of just having it in general times the 80% chance of it actually being a positive test.
Okay, before
Or
you even do
correct,
that, I'm just
accurate.
gonna break it up. Like 99%
Yeah.
of people don't have the allergy, and 99% 99% don't, and 1% of people do. Okay, so
Yep.
now the allergy branch, we can break that up even further. So what were you saying there? How do we break it further?
I didn't really break it further. I kind of just multiply, or, oh, no. Okay, I see what you're saying. So you'd break it up by if the test is accurate, the 80% chance, and then if the test is inaccurate, the 20% chance.
Exactly. So I'm just going to do tested positive or negative on the test. So this is the test, and this is the actual condition. And what they told us here is that this is the probability of a positive given that you have the allergy. And I don't like, with these problems, I really don't like to go too much into the formula, because the formula, if you just memorize how to use the formula, it's actually really quite confusing. But the tree diagram makes it a lot easier. So therefore, the total percent of people that tested positive when they have an allergy is going to be 0.1 times 0.8, which is 0.00. Oh, can I move this whole thing over? Which equals 0.008.
Wait, 0.1 or 0.1? I mean 0.01.
Oh, 0.01, thank you.
Yeah, okay. I'm just confused.
0.01, so we want to move, 2 spots over, 0.008. So it's 80% of 1%, so it's 0.8% of the overall population would have the allergy and then go for the test and get a positive result. And then, Adam, what would you get for the branch below it? Not that it's super important, but what would it be?
It would be 0.01 times 0.2.
Awesome. Okay. And then how about for the no allergy people?
For the no allergy, the two branches would be if the test was positive and negative, and if it was positive, it would be a 0.1% chance.
Nice. And we take 10% of the 99 people, or 99% of people, which is about overall 9% of the entire population. And then for the negative,
it would be 0.9 times 0.99.
Excellent. Did you calculate this one?
No, I didn't. Here, I have a calculator. 0.891.
Okay, good. We actually could have, you see a nice way we could have done it without a calculator as well?
Maybe.
All of the things in this, all these numbers, because they actually represent percentages out of the entire population, they have to all add up to 1. And this is, it's going to be close to 90% because this number is close to 1, but you could figure it out that way. But excellent.
Okay.
So what numbers did you now work with? What branches are really important for us?
The two branches that are important are the two ones that came back positive.
Excellent.
Since we know that he had a positive test.
So we're in the positive universe now. And what ratio do you use?
I just did 0.008 plus 0.099 at the bottom of the fraction.
Uh-huh.
And then at the top, I did 0.008.
Excellent. This is the probability and I'm gonna write it a little bit using the formula, but Adam, this is the way that I think about it. I don't really do a formula. I think about like what my branches are, what universe I'm in. Okay, I want to know what's the probability of having an allergy given that I'm in the testing, like out of all people that test positive, how many of those have the allergy? So you don't really need to get into all these formulas, but oh, by the way, when you calculate this, what number do you roughly get?
It was about 7.4%.
Nice. So 0.074. So this is 7.4%. So the chance that you tested, if you tested positive, the chance that you actually have an allergy is really, really low, 7.4%. And I'm just going to quickly write the formula here. So the probability of allergy given that you tested positive is equal to probability of allergy times probability of positive given allergy, and the denominator is probability of not allergy, so I'll do allergy complement times probability of testing positive given that you didn't have the allergy, plus this other term, this original item, this first branch. So copy and paste. So that's a little bit messy, but the denominator is this kind of big expression. But all it is the sum of the two green branches is the denominator, and the numerator is the branch where you tested positive and you had an allergy.
I'm a little bit confused about the last step. So I was able to get to 1.07%, which is just the denominator. And
Okay,
I just don't understand why it's the 0.008 over that.
good. So do you see that the denominator is like out of the entire global population? If you gave the entire global population this test, you would get what was it? About 1.07% of people would test positive if you gave everybody the test. So that's what you
Is
calculated.
that what that is? I thought 1.07 people would have it.
No, 1.07 would test positive, regardless of whether or not they have allergy or no. Because 0.008% of people test positive when they have the allergy, and 0.099% of people test positive when they don't have the allergy. So you
Yeah,
can
I was
imagine,
thinking about it like those two like test positives were people that actually had the disease. Actually had the allergy, not those are the test results.
right. Yeah, it's exactly. The thing here is that testing the test can give you some false signals about the underlying condition. That's kind of a big thing. And we're using kind of the information that they have from the laboratory where everything is controlled to figure out in the actual world, if we get a positive test, how we should interpret it.
I have a question. So the 7.4 is that you tested positive and you actually have the allergy?
That would be 0.008. So like less than 1% of people have an allergy, and like out of the entire population, less than 1% of people have the allergy and test positive, because only 1% of people have the allergy. The 7.4% is a conditional probability. So it's out of all people that got a positive test. So you got a positive test. You're no longer kind of in the global population. You're in a subset of people that got it tested positive. So in that subset, which are the two green branches, so out of those two green branches, how many people, like what percentage of people actually have the allergy?
Thank you. Yeah, that makes sense.
And what do you guys think? Is this number surprisingly low for a test that seems pretty good? And can anyone offer an explanation why this number, like if you went and you got an allergy test and it's positive, you're like, oh man, I have an allergy, but in reality, it's only like a very low chance that you have the allergy. So what's happening here? Why is this argument showing us that there's such a low chance? What's so weird about it? Or what's causing this effect?
I can try and say it. I might be a little inarticulate, but like if you had something where like only one person had something out of all of 7 billion people,
Yes.
if your test was 99.9% accurate,
Yes.
you would get far more people who don't have it but tested positive than you would get the one person that had it.
Excellent.
Just because of how vastly small that is. So when only 1% of people have something, you'll get a lot more false negatives.
Excellent. Yes. Awesome, Quentin. So when you have a really rare condition, even if your test is super accurate, the false positives on that larger population that doesn't have the disease, they'll give you a lot of positives overall in the population. So if you're interested in the chance of having something, given that you test positive, the positive universe is way larger than just the people who have the disease and test positive, because the positive universe has been overweighted with people that got false positives. So this is particularly important to be aware of if you're testing for really rare conditions. If you test positive for a really rare condition, you might want to kind of do an alternative test or test it again. Don't just jump into a conclusion based on that one test. Okay, do you guys have any questions? I'm going to post some practice problems from a website that I like, and maybe also some questions from Khan Academy. You can try to do this question, like if you want to watch the videos and set it up with the formula. Try to make sure you understand what the formula is saying and what it how it connects to the picture. But when you're solving it, just draw a picture. Either some people like to draw a table. You can also do it with a table. But write it out, visualize what's happening, think about the categories that you're talking about, and that helps to make these kind of questions very clear and not as confusing as just plugging in stuff into a formula where a lot of things are being switched around, which to me looks super confusing. All right. I'll hang out if you guys have any questions, but otherwise, I hope you guys have a great weekend, and I'll see you on Tuesday.
Bye, thank you.
Thank you. Bye.
Thank you.
See you.
Thank you. Have a good weekend.
You too.
I also have a question.
Yes, Quentin, what is it?
Yeah, I missed class and I was checking Classroom and I noticed there's a Google Classroom assignment for Khan Academy.
Oh, yes.
I didn't hear about. Could I just briefly hear what that is we're supposed to be doing?
Oh, yeah. Hang on. Have you added yourself to the Khan Academy
No.
class?
If we
Okay.
did that in class, I wasn't there for it.
Yeah, I don't know if I mentioned it or it might have, let me just share my screen really quick. So I have a, where is it? Classwork. Yeah, I probably should have. So I did, where is it? Syllabus? No. Oh, this is Math 96, my bad. Yeah, the wrong. Okay, so yeah, resources, go to Khan Academy. Do you see this code here? CAKY8SKS?
Yeah, I see.
So just add yourself, and once you add yourself, I'll log in and I'll add you to the class, and I'll send you all the assignments. Don't worry about the assignments that are about combinations and permutations. Just do the recent ones about probability. But they're also pretty straightforward. I don't envision it'll take you more than half an hour to do them or something.
Okay. Thank you very much, Daniel.
Definitely. Well done.